So today we're going to cover easy stuff, which is nice because if we don't get to chapter 10 today, we'll be covering that in the next class. That is actually going to be a somewhat more difficult one. And the reason why it's somewhat more difficult is because the concept of collections, if you've done any programming, you already have. The concept of generics is one that you probably don't have unless you've worked in a language that supports it. And the amount of languages that support it are very few and far between. And the amount of languages that actually push you in that direction, it's probably literally just C++. Collection is a method of thinking of an organization of data. And when you think of data as being already organized, there's a lot of things you can do on it. And we'll cover some of that. Generally speaking, all collections have a map method. And when you start to wonder what map does, you can learn a lot about these dynamic of a collection. And if you have one thing that's returning a collection, that collection can mutate over time into a different collection. And you can call map every step of the way, right? So there's these functions that just simply ask for a collection. And the collection gets to define how that functionality is implemented. And that kind of makes it a unifying concept in Rust. It is somewhat, I would say, like a more abstract method of what Python does. Python has this notion of an iterable. And for Python, you start to break objects down and problems down by things you can iterate over. Okay, so a collection is something similar to that, but it's less direct. And in this chapter, we're actually going to go over how Rust does iteration, and it's very similar to how Python does iteration. But Rust has taken this one step further, right? And you have these other things like map, and we'll cover some of that too. It right. Let's go over some of these examples. Vector has multiple different things inside of it, right? And because it contains these multiple different things, there's a lot of different functionality we can call on a vector. And we went over this before. I'm using this Rust extension to see documentation. So if I want to see documentation, I open up a new tab, rs space, and I can just say vec and enter. And of course, it never works the first time. That's a problem on me. I haven't figured it out yet. But you'll see here that this is module std vec, a continuous global array with heap allocated contents written as vec_t. Chapter 10, we're going to learn what that t means, right? And on the left-hand side, you're going to see these methods that should be implemented by it, or traits. Let's see here. Oh, here. You can explicitly create a vec. There we go. So here's actually the struct for the collection. And on the left-hand side, you're going to see all the different methods that it provides, right? And you'll also see all of the different traits that it provides too, trait implementations, right? And these are the different things that your collection can act as and do. So these are like pieces of functionality that the vector implements. And this is somewhat useful, and it's kind of cool, because if you think of a vector as something that contains data, right? You can get to a different abstraction where you have a vector that allows parallel iteration, right? So there's a whole library around that in Rust. It's called Rayon. We're going to cover some of this stuff, I think, when we're done with the class and we get to geek out. But Rayon is really cool because let's say you have a vector and it contains 100 different things in it. They're all the data to assemble a vehicle. They're attributes for a vehicle. You can iterate over each different one of those with a for each loop. And you can say, I want to create this vehicle with this data I have that represents a vehicle. That may take some churning. There may be some calculations done. Okay, but you can take the same vector, right, and now make it a parallel vector with Rayon, and then you can do parallel iteration over the vector. And it doesn't require any more code. You wrote your code to implement with a vector, and suddenly there's this thing called a parallel vector. It works almost the same way, provides almost the same interface, but now it has parallel iteration. And you can just say, do this to each different member, and it'll take care of making sure that that code gets scheduled across all of your different cores and your CPUs, and it'll all happen relatively seamlessly. So for doing this computational work, you can unify behind these collections, and we see a lot of that in more advanced Rust. And that library is called Rayon, And I'll show you kind of how that works here, because it's pretty geeky but fun, and it's very easy to wrap your head around. So there, you can see what I'm looking at. OK. So there's this, let's see here, parallel iteration. So here's an example of kind of how that looks, and we can see here what I'm getting at. Sum of squares takes an input, which is the slice of I32s, and it's returning an I32, and we say on that thing you're providing, we're going to call parallel iteration on it, right? So now the difference is that input, rather than it being a regular array slice, is actually this special rayon thing. And now rather than having iter, it has iter, which is parallel iterization. And it's doing the same type of work. It's saying for every different element in that array, I want to take each different value and I want to multiply it by itself, right? So effectively we're squaring it. And then we're summing all of the different values that are returned. So you can either do this for every different item in procedurally, one after another, or you could do this with it for every item in parallel, right? And how we do that is we take this notion of a collection, which is a vector, and we re-implement it to be a parallel vector with this rayon library. And this allows you to write very complex programs using just rayon voodoo, and other people barely even know that it's not a list, you know? And they work the same everywhere. Cool stuff. All right.
Still running one thread right now. This code?
Nope.
Oh, it's running all of them?
How many threads do you use?
Yeah, how does it
There's different settings for that. So it's effectively like a global. It's kind of like OpenMP.
But the sum has to wait for it.
Yes, the sum is waiting. Yep. But the actual iteration on the array is not waiting. Actually, I'm not even sure that the sum is waiting. I think it's actually consuming the values as it happens. But anyway, we'll geek out with this kind of stuff later. If you're interested in it, look at rayon. I don't want to get too much into it. I'm just saying this notion of we can treat something as a collection, iterate over every element in it, square it, and then sum them all together. That's a series of different operations you're doing on that collection. Square every element inside of it, return all of those elements, and sum them. With rayon, we just modify the way a collection works, and now it's parallel. Cool. So we have this vector, we have a string, we've already covered strings, we'll cover them more today, and we have this notion of a hash map, and there's a lot of things we can do on it. So for instance, if you iterate over a vector of things, you'll get every different item. If you iterate over a hash map of things, you'll get the keys and the values, right? So there's different ways we can do that too. All right. Creating a new vector, we've already seen this code. This is actually a strongly typed vector because we're saying that that vector is I32. All vectors in Rust are strongly typed. That's not the right word. What I should have said is this is a vector that is not inferring its type. This is an explicitly typed vector, right? And why would I say that? Because there's no such thing as an untyped vector in Rust, right? So when we say here that this vector is of type I32, what we're specifying is in the future, when we fill this up, the things that we're filling it up with must be I32s. And if they're not, they must implicitly convert to I32, or you must do the extra work for it. Does that make sense? OK. Here's this vec exclamation point. This is super helpful. Why is it helpful? Because we can make a strongly typed vector, but that is wrong word again. I'm sorry. I'm trying to be very careful about this. We can make an explicitly typed vector, but that's a pain in the ass. Why? Because if we already have the types of the variables we're providing it, we may not want to say that the vector contains that variable, right? We may just want Rust to go figure it out. And how can we do that very effectively? With the vector macro. The vector macro can look at the different types you provide in that macro and say, I want a vector of this type of this size. So it has two different pieces of information you can't get without using the macro or without putting more work into it. The vector macro knows how big that vector's got to be the second you spin it up, and it knows of what type the elements are inside of it. So it is a way for you to give that information to the compiler, and it reduces your amount of work. Vec : new, explicit typing, all that other kind of crap, or vec exclamation point, don't worry about it. Same effect, right? So we have a notion of a vector, and we can create a mutable vector or an immutable vector. If we come up here, you'll see that v is not a mutable vector. What does that mean? It means that that vector can't shrink or change in size. It's this fixed size. The one below it, though, we're declaring a mutable vector. We say the mutable vector v, right? And again, in this case, we are not giving it an explicit type. We are letting that type be inferred by the compiler based on what you provide to it in compilation, right? So here we're saying vpush 5, 6, 7, 8. Rust will look at that. It'll say, what type is 5, 6, 7, 8? Based on that type, it'll set the vector to be that type. That type can change. It doesn't have to be the same. I don't think it has to be the same. In fact, I'm 95% sure it doesn't have to be the same. If you compile Rust on a different platform, I think it can have different types for it.
You can still overwrite the elements of the immutable vector?
It says here, yeah, it's mutable. You can remove them, do whatever you want.
No, the immutable, you can overwrite the elements.
The vector itself is mutable. The types inside of it are not. You know.
So the first one, so without the mute, you can still modify the elements. Mutate the elements. You can't just
There is something called intermute, which allows you to change the actual elements underneath. Yes. Is that what you're getting at? You want to know how to change the elements underneath?
So you can't change it. You can't change the elements if it's not mutable.
You cannot change the elements if it is not mutable. That is correct. Yes.
Like JavaScript has a constant keyword.
Well,
But you can change the things.
there is interior mutability, right? So there's other types that have interior mutability, and we'll go over them later. But we're not going to go over that right now. There is effectively a way out of this problem, and we'll work on that later. All right. Or just do a search for interior mutability, and you can read about it now. It doesn't make a difference. With the numbers we place inside are all type I32, and Rust infers this from the data, so we don't need the vec I32 annotation. So what they're saying here is that they don't need this vec I32 annotation. This is what I was calling explicit typing, right? That's not to say it's not strongly typed. It is. Either way, Rust has to have that. But the lack of the annotation means that Rust will infer the type from the arguments you provide. Now, I don't know that this is I32 on every system. In fact, I don't think that's actually true. But if you're compiling on an Intel or an AMD machine, it is certainly true.
Is there a benefit to just using, like, explicitly declaring it as usize instead of letting it infer that it's going to be like I32 or something?
I don't think usize is strongly typed either. I mean, I don't think that usize is universal either. That's the architecture's most optimal size, which is specified by the different architecture.
Well, that's my point. If it's going to infer from an integer that it's going to be I32, is there a benefit to say use the architecture's most?
I don't think this part of the book is right. I think that it could change based on the architecture.
So you think it's already like going through usize or isize, whatever?
Kind of, yes and no. I don't think that usize is necessarily the type that it has there, you know. Okay, anyway, let's go through this, because there's a difference between the size that's required to store a pointer and then the size that the computer is best optimized for. But those are all questions that I think are way outside of this class, you know. So I don't want to get too far into it. Okay, let v equals vec, and then we have 1, 2, 3, 4, 5. We are storing 5 different elements inside of a vector. We are taking the third element, which is a reference to an I32. And notice that the third element is the second index. Everyone should know this. Why? Because in every language in a computer programming context, 0 is the index to the first element in the array. So they're always 0-based. And cool, easy enough.
Except Excel.
Well, we're going to pretend like that doesn't exist. There are other languages, too, that have violated this commandment. So we have third option. We take an I32 and we say v.get 2. And then what we have here is this time, because we're using get, we're getting back an option, right? So the thing to note here is that in most languages, you're going to index it into an array with a bracket, right, or a vector with a bracket. And you're going to get back the element at that index, right? But the question is, what happens if you give it an index that doesn't exist?
Crash.
Right, exactly. So Rust is going to panic if you use the bracket. And if you use .get, you have the option to recover. You can say that element doesn't exist, and that's what we're doing here. So v.get is returning an option. It is not panicking. There is no way .get can panic. So it's returning an option, and if you don't get something back, you can say none. There is no third element, right? Right?
You have to do like a .expect from the get.
Yeah. Well, I mean, you shouldn't do that. You should always avoid panicking, right? You should avoid anything that can panic in your code. That's the general rule. Now, do people do that? Of course not, because it'll drive you nuts. So the thing is that the question is fundamentally, who's going to consume this code and how much do you care? Now, on that, I can provide you one piece of guidance. If you're providing a library for programmers, they will always care. They will bitch. They will complain. If you are providing a utility for end users, they're only going to complain when it barfs on your screen, right? So if you are reasonably sure that it'll never panic and you're providing an end utility for a user, then you can cheat. But if you're providing the ability for a programmer, they're going to complain if you have panic code. You need to handle your exceptions. There's a social pressure there. All right. So note a few details here. We use the index value of 2 to get the third element because vectors are indexed by a number starting at 0. OK, we just went through that. And I already explained that. The reason Rust provides these two ways is to reference an element so you can choose how the program behaves when you try to use an index. Gotcha. Nothing complex there. Here we have an element with 5, and they're showing you that because we do v.get on the bottom, we get that option back, and it's going to be none. But the one right above it, that is actually going to panic. And it is actually going to panic in compile time, right? So in this case, Rust can link the two together, and it will know that the code doesn't compile. Now, it's also important to say that Rust can't always catch this error in compilation, right? So it can't always know how many elements are in a vector. If you are adding to a vector based on something you're receiving in I/O, like a database, you may not know whether or not the database is returning a row. So if you call, for instance, query.get, and you want to get the first row, query.get 0, you may get none. But if you call query brackets 0, and you want to get the first element that way, it may just panic. And it will not panic in compilation in that case, because compilation doesn't know what your database has got. So some things it will catch, and other things the compiler won't catch. And this is the compiler aggressively catching it, effectively. All right, and here's another one. Here we have a vector macro. We have 5, and we are saying the first is the 0th element, and we're pushing onto it 6. And we're saying the first element is first, right? So here's the error that we're getting. Immutable borrow occurs here. Mutable borrow occurs here. So it's telling you, again, we had this notion before when we were covering how Rust ownership works. And we said we can have as many copies of a reference as we want, so long as they are immutable. Or we can have one copy that is mutable. We can't have both, right? So they're showing that in this case, first is an immutable borrow of the 0th element, the first element. The first element, the 0th index. v.push is requiring a mutable reference to the vector, because .push would be implemented asking for a mutable reference to self, and that can't exist at the same time. So we have this error. OK? Now, there are very easy ways to get around that. The book doesn't go into that, apparently. Unfortunate. If we want to get around that, how do we do it? Does anyone remember? Clone, right? If we clone it, then we have an additional copy. And the second we clone it, we no longer need the immutable reference. So the compiler can say, he's not using the immutable reference. I can get rid of it. Now we have a copy of the first element, and then we can push on the latter elements, the other elements of it. Iterating over the values of a vector. Here's where we are implementing the iterable trait, right? So this is I think, the simplicity of Python. This is one of the reasons why I like Python. You have this notion in Python of a thing in which you can iterate on. And here we have this notion of a vector, which is something we can iterate on. And it is done through a trait which provides for iteration. And how that works underneath the hood is you ask the vector for next, and the vector provides to you the next element. So the first time you call it, you say, I want an iterator. The iterator stores its state of what you're processing, and then you can call next and advance that state every time. So an iterator for a vector may say, I have an index. I'm starting at 0. and then you call next on that iterator. It says, OK, here's the first element. I call next again. Here's the second element. I call next again. Here's the third element. And every time you call next, you're either going to get an element or you're going to get none. And that thing, that unit of behavior of iteration, can be applied to all collections, even collections where it doesn't make necessary sense. And what do I mean by that? I mean, for instance, sometimes it may shock you. I believe you can call next on an option and get the first value in the option. Can't call it a second time, but you can call it a first time. Why is that sometimes useful? Because it allows you to not know whether or not the collection you're getting back is an option or a vector. You can always call next on it and see what values it has. You can start to think of it as, well, if I have a value, I can call next on it. I can get an iterator from it and call next on it. And I don't care then whether or not it's an option or a vector. You can start to think of an option as having a vector of one value. It may make sense in some contexts. Here we're taking it and we're doing this let mut v equals vec, and we have 3 different elements we're assigning to it, and then we're saying for I in mut v. And in this case, we're dereferencing the reference we get back, and we're saying plus equals 50. And this is getting to Kai's question earlier, right? How do we mutate the elements inside of the vector? And I said that there was a trait underneath the hood called itermut, and this is what this is using. So not all vectors have this ability to do this, but no, let me correct that. Not all collections have the ability to do this, but a vector does, right? A mutable vector does. So using enum to store multiple types. All right. So we covered enums in the last class, and now we're creating a spreadsheet cell, and it has 3 different possible ways to construct a spreadsheet cell. We have 3 different type constructors for that type of spreadsheet cell. The first type constructor is called int, and it takes an i32. The second type constructor is called float, and it takes an f64. The third type constructor is called string, and it takes a string. One thing to say here is that in this type of spreadsheet cell, we have to own all of our data. The world will come crashing down, and you'll get a lot more complexity when that is not the case. That is what chapter 10 is about, right? Chapter 10 is about showing you what it's like to not have to own the data. But in this case, we own the data. So we're creating here a vector, and we're creating 3 different elements in that vector using 3 different type constructors for the type spreadsheet cell. And this is what it looks like to do that. Cool. All right. Dropping a vector and its elements. That to me is not all that useful. Everything in Rust that is owned gets dropped when it goes out of scope. So yes, a vector is like anything else. When the collection goes out of scope and nothing owns it, Rust says it's time for you to go. And that's how the compiler handles it. And it can determine all of that in compile time, because the scoping is known at compile time. So the second this v is no longer in scope, it's going to get dropped. That memory is going to get freed. And what happens to that memory at that point is a big question mark for the purposes of this class. We can cover that later. But it's effectively the compiler questions that you were asking about, Brian. It has a lot of leeway to do different things with that.
Was there an extra HDMI cable that ended up in here somehow?
Potentially, yeah.
Yeah, short one, but
I don't know that that's the short one.
doesn't matter. Just need one.
Well, I think you're going to have to, yeah. If you don't want that piece.
Okay. All right, thank you so much. Appreciate
There
it.
you go, no problem.
All right. Sorry, folks. Thank you.
No problem. Storing UTF-8 encoded text with strings. Yeah, Rust is going to keep this part of strings. They actually do, right? And this is one area in which, how many people here come from Python? We have Python users here? A couple Python, half the class Python users? OK. Any Python users around before Python 2 and Python 3 Fiasco?
2.7.
OK, well, if you have any experience with Python 2, This is Rust saying we're not Python 2, right? Python 2 didn't have a notion of what a string was different from a series of data. It had a notion of a collection, and a collection was just simply relatively untyped stuff. It created a lot of problems in the language, because you want to take a string or you want to take raw bytes, you may treat them fundamentally different, right? Rust starts off from the get-go, and it has a notion of a UTF-8 encoded string, and that is the only notion of a string when we say string like that. There are other types of strings which provide strong typing in other contexts, right? But this gets very confusing, and Rust does this. It is an immaculate way of doing it. It's very nice. And I'll give you some ideas of why that's nice. Think about all of the different ways that strings can be represented in the course of a program. You have like your file name, right? The file name in your program. That may not be a UTF-8 encoded string. It may be a UTF-8 encoded string, but there's also going to be characters that aren't allowed in it. There's going to be all different types of impositions on it. So the notion that you create a file with a UTF-8 encoded string is probably wrong. Rust does this right. You create a file, you have a different notion of a string. When you communicate with an external library, a C library, the C library is almost certainly not going to be using UTF-8 encoded strings to pass data. When a C library says a string, it's almost certainly just going to mean bytes. So Rust has all of these different discrete typings of this collection, right? And it's saying that in the default, the string type you'll encounter most often, it's UTF-8 encoded. So we have a notion of a vector, which is a collection of any type of data, right? And we have a notion of a string, which is a collection of UTF-8 encoded data. And they're strongly typed either way, right? So when you say you want a string, it is different from a vector in the sense that a string, when you construct it, has to be strongly typed UTF-8. And what does that mean? That means if you look at UTF-8, there are character sequences that are invalid in UTF-8. You can provide UTF-8 data you can provide data to a UTF-8 constructor and get invalid data back. So Rust, when you create a string, it makes sure that that string is UTF-8 data. And it does that when you construct it. And that's why a string in Rust is different. It's a specialized case of a vector. That's how I'm going to say it. It's a specialized case of a vector. A vector that can only be constructed with UTF-8 encoded data, that's what Rust calls a string. OK.
Could you cast all of the elements of the vector into UTF-8 and then remake it as a string because you hate your data?
Can you do what now? Say it.
Could you recast all of the elements inside of a vector to be UTF-8 strings and then construct a string out of a vector?
You cannot. No, you can only, a string can only be constructed with strongly typed, it's not, they don't call it strongly typed. I think they call it, it's basically valid UTF-8. A string can only be constructed with valid UTF-8. If you try to construct a string with invalid UTF-8, when you do that, Rust will say, this is not valid UTF-8. I will not allow this, and it'll panic, right? There's also safe ways to construct a string that won't panic, but I think that's the default behavior.
Type convergence between a string and a vector?
The ones they provide as safe type conversions will check. So if you want to convert between a string and a vector, that is always safe. Why? Because a string is a specialized vector. But you cannot go from a vector to a string without Rust ensuring that you have strongly a valid UTF-8 inside of it. Does that make sense?
Yeah, that makes sense.
So it's one way, right? All right. Creating a new string. Here we say let mut s equals string new. This is creating us a string type, and we're giving it some data. We're saying, well, no, this is a different example. Yes, OK, different example. Let data equals internal contents, data to string, right? This method also works on literal strings directly. OK, so what they're showing you here is that the one above is a string slice. Let data equals that thing above it is a string slice. The one below it, when you say data.toString, you're getting a copy of an owned string. And the difference is this one here, this literal string, right, this string slice doesn't give you the ability to push to it or mutate it or anything like that. The actual toString method is returning a string. You can do that. Here's another way to do it. If you need to have a string in which you own the data, you can call string from. We already went through this. You can provide it a literal inside of it, a literal string inside of it, or a string slice, and Rust will construct that string for you. OK. We say here, let hello equals, and now we're giving it a string in all these different languages. Now what's key here is that all of these different languages must be UTF-8 encoded in your source code, right? So if you're writing source in something that's not UTF-8, and it's some other predecessor UTF-8, you're going to have to make sure your source is encoded in UTF-8 in order to make that work. Because string, it's looking at the actual bytes in the source. An updated string. A string can grow in size and its contents can change, just like the contents of a vec-t. If you push more data onto it, OK, obviously, we already went through that. So this is the notion of this s.pushString. And this is the same thing as using the concatenation, right? We talked about you can concatenate to a string, but this is not an optimal method. It's not something Rust encourages. Why? Does anyone remember what Rust does encourage to do this?
Format.
Boom. He's paying attention. Good. The format macro. Format macro allows you to say, I want to take all of these different string elements, and I want to make one big string out of them. So Rust as a community has somewhat pushed behind the format macro because it eliminates the intermediary steps of concatenation and pushing. OK. All of these lines, S will contain foobar. Yes. The pushString method takes a string slice. Gotcha. OK, so in this case right here, we create this new mutable string called foo. We say s2 equals bar, and then we call s1 pushString s2, and it's printing out s2 is bar. And the reason, I don't get what they're trying to show here. That's so obvious. What's the deal?
I think they were trying to say S1 goes out of scope, I think.
Ah, OK.
S2's value is already out of scope.
Yes. No, what they're trying to show here is that pushString is not taking by ownership. It's taking by reference, right? So the pushString method takes a string slice, right? And a string slice is a reference. The string slice is the ampersand str type, right? So because you're taking it by reference, you don't actually take ownership of it. And they're trying to show you here that when you add S2 to S1, S1 is taking that reference to it and adding it to your mutable string. That data is getting effectively pushed onto your mutable string. And when it does that, it is not owning S2, so you can later still reference it. And yeah, so there's also a push method. The push method takes a literal character. So we have this pushString method, which is taking a string slice, and we have the push method, which is taking a character. I don't think you'll ever use this. This is not very valuable. Has anyone ever built up a string one character at a time? I don't think it's going to happen too often. Well, maybe, But I'm saying it's not a very common thing. But yes, you can do that too. OK, now we're getting back into the format. We've seen this before. I don't remember if we saw it before, if I just showed it to you. But with Rust, we do a lot with this format macro. Here we're creating the first string, hello, the second string, world. And we're showing you that we can say S3 equals S1 plus a reference to S2. And S1 has been moved into S3, right? So they're showing you that at this point, the data from S1 it's now owned by S3, but you're not providing this S2 directly. You're providing it the string slice, right? You're providing it a reference to S2. So because you're doing that, you can still access S2. And you can see that here with add, right? So the add operator is taking, the add function is taking self, it must own, right? And then it's calling, it's taking a reference to the string. So again, we talked about this briefly before. I said you can tell a lot about what a Rust program is doing by just simply reading the type, right? So the very fact that add is owning self, right, and it's taking a reference to the other thing you're adding, tells you a lot about how add is working. So when you call S1 plus S2, what Rust is doing is saying, wait, that is just sugar. This actually works very transparently under the hood. S1 plus S2, as it's written right there, is calling S1 dot add S2, right? And this is how that looks. So the top, this syntax S1 plus, is effectively this on right underneath it. It's effectively this. And that is something to see everywhere in Rust. A very lot of things that you do in Rust are just sugar for things that are implemented like traits or macros. A lot of Rust is sugar for traits and macros. I'll give you another example of something that is entirely sugar for a macro. Question mark. You know, question mark looks like it's a lot of voodoo under the hood, but it is just using the try macro, right? And that doesn't, you should never use the try macro anymore because, you know, anytime you write a try macro, you're almost always just better off putting the question mark in there. But I'm saying that a lot of this stuff that makes the language look beautiful, terse, right, very easy to follow and read, a lot of that is just expanding to something like this. Okay, and I'm going to say one more thing about this too. This notion of add right here, this, like everything in Rust, is this, the traits, right? So if we come up here and we say rs, and I want to just look up add, you'll see here trait std ops add, and here we have a trait, and this is what it looks like, right? Let's say you take your own type, and you have a type, and it represents a receipt, right? And you have everyone at the table, they all get their different receipts from their different meals. And they want to, one person wants to pay. You can implement the plus operator, right, using the add trait for a receipt. So you can make it to where this notion of plus receipt 1 plus receipt 2 plus receipt 3, that this works, even if the receipt represents a whole struct of data. How do you do that? You have a struct of data, it represents your receipt, and you're going to implement the IMPL thing. We saw it earlier. We saw how to do it with debug when we were talking about how do I make this struct print out this type of text when I want to use the print ln on it. We implemented debug and display on different things. We did that in an earlier chapter. The same way we implemented debug and display to say this is how I want my types to print out, we can implement the trait add and say this is how I want my struct to behave when it's added to another struct, right? In this case, add is saying that you're adding the right-hand side must be of the same type, but it doesn't have to be of the same type. You can implement add for your struct and someone else's struct, right? So it's a very powerful syntax you have here. Let's say that you want to take the receipt, which has all of your data about your meal and only the total represents everything on it, and you want to add it to something else, which is like a banana and it has a cost, right? You can do that. You can say implement add for receipt where the right-hand side, rather than equal self, equals banana. And then you just look at the cost of that banana, you know, or whatever, item. And you can have it work with two different types. So when you see it and you present it to your user, you could just say plus, and it just works, and it does whatever they want. But this is how simple that's got to be when you implement it. You just have to say what the type is you're adding it to, and how it's going to behave when you do the addition. Anyway. So I only showed you that because I don't want you to think that all of this voodoo for a string, where it has add, is something that's unique to a string. I want to get out of that mindset. Rust has very little in the way of specialization for anything. Everything you're doing in the core library to provide this functionality is something you can do in all of your own code. Yes?
Is this trait bidirectional? Like, would it work if you add banana plus receipt when you implement the trait only for receipt?
I don't want to speak out on that one. I don't want to speak out on that one. I am fairly certain that it implements by default the reciprocal trait, that it also allows you to override them. Does that make sense? I'm 80% sure that's the way it actually works. And they have a whole method of doing that in more advanced Rust. The question is, the addition operator in math is, okay, by the way, I did a whole entire like raging class one time where I think I called it math terms are stupid. So the fact that A plus B is the same thing as B plus A, there's a name for that. Who's a math guy? It's which one?
Identity property.
Nope, that's not it. I don't think that's it either. Commutative. I think that's it. I'm pretty sure that's it. I think the associative one is the parentheses. You know, A times A and then in parentheses BC is the same thing as AB times C. I think that's the associative property. Yes, the commutative property, or whatever. I don't know. Communism's better. But the point that I would make here is that the idea that A plus B is the same thing as B plus A is true in math. It is not necessarily true in programming. You can have, I believe, non-commutative addition. Very geeky stuff. But anyway, that's the answer to your question. Cool. OK, I'm getting thumbs up. I'm moving on. We also have here S1, S2, and S3, tic-tac-toe. And what we're doing here is we're saying S equals S1 plus hyphen S2, and then so on and so forth. We're concatenating all of them. And it's effectively saying that this is a slower and less efficient way of doing this format thing below. You're telling the compiler less about what your resultant is, and you're instructing it to create these intermediary steps. Why are these intermediary steps being created? Because we saw, this is actually good, right? This is where I can talk about like that whole tangent and make it useful. Add here doesn't know what comes after. If you say A plus B plus C, there is nowhere C gets factored into add. Very transparent. This is the shortcoming of that Rust has, because the language is so transparent, that other things may not have, right? Other things like Python have the ability to see all of the shit you're adding together, and then it has a special opcode in Python, which is like add multi or something like that, and then it provides all of these different arguments for it, and add multi knows how to handle all of them. Rust doesn't have all of that kind of stuff, and it doesn't have that kind of compiler optimization. So Rust says, I have A plus B. A is self, B is this right-hand column thing. That is going to return self-output, whatever you set self-output to, right? Then I have the output plus C. And how am I going to do that? Well, this time, when I have the output, it's going to be self, because now it's on the left-hand side. And the right-hand side of that is going to be that C, right? So you have two different calls to add in A plus B plus C, right? A and B produce an output, then that thing plus C. And what they're showing you here is that this is effectively why we don't do this with strings, why we use the format macro. Format macro is our method of getting around that. All right. So we have here string from hello, and we're saying here S1 equals 0. This doesn't actually work in Rust. Why? Just because that's the design decision of the language. There's no real reason for it. I mean, certainly in a lot of cases it could work, but in Rust, they just simply say that that's not valid. And this is what you get. A string cannot be indexed by an integer. There are other ways to do what you want to do that are clearer than this. I grant them that. But the reason why this doesn't work is just simply because that's how the language is built, and it's totally arbitrary. Right? In other parts of the language, this would behave differently. Does that make sense? Do you understand why I'm treating like this? There is no reason why that couldn't have a behavior. It is cleaner to tell it explicitly what you want than for Rust to make an assumption. So in this case, Rust doesn't make an assumption. It could have made an assumption, it just didn't. And when I say Rust didn't make an assumption, what I actually mean to say is there is a trait called index, right? And that provides get. And Rust simply has not implemented that trait for the string type. And if you wanted to implement it, and just to take it to like, because what I'm trying to show you is that this isn't really voodoo. If you wanted to implement it, you could fork Rust. You could go into your std : collections : string, and you could simply implement it yourself, and it would totally work. And that's all it would be. Just saying, Rust has made the decision not to do that because there's cleaner ways to do it. Okay.
But Evan, from what I understand, the reason why Rust didn't do that was to prevent other problems down the road that could happen based on the way that Rust handles strings and the complexity behind it with UTF-8 and a character's not always a character and all that,
A character's not always a character, but sometimes it is a character.
I know.
I'm just saying, so I'm saying they could have just said, well, let's just assume it is a character and then panic if it isn't, right?
Yeah.
I'm just saying they do that with arrays, right? If you take a vector and you index it, Rust doesn't say, well, what happens if it's not an element? We're only going to allow you to get this option back. Rust didn't say that. They said, we're going to assume the element exists if you try to index into an array, and if it doesn't exist, we're going to panic. And that's what happens. And Rust made the decision there to allow panicking to happen in runtime if you use that operation, which may be unsafe. But they chose not to allow an unsafe operation in a string, and there is no really good reason for it. I'm just saying, I just don't want people to think that there's like a reason why.
So if there is a reason to do so, like pattern matching or anything, or getting the element.
Right. Okay, so the question is, if there's a reason that you want to index into a string, can you do it? Yes, you can. Why? Okay, because a string fundamentally is there's two different ways you want to process a string, right? The first way you may want to process a string is by looking at the actual bytes inside of the string. You may want to process one byte after another byte after another byte from the whole beginning of the string until the end of the string. You may also want to process the string by characters, where you process one character and then another character and then another character. So there are two equally valid ways to process a string. One of them may produce for you bytes that are not a full character. What does that mean? Well, sometimes you have UTF-8 and you process, the great thing about UTF-8, if anyone knows how does anyone here know how UTF-8 works, or we have some background in it? Effectively, in UTF-8, you have these things that are effectively characters, and they can be up to 4 bytes big, right, in UTF-8. And then you can stack on additional characters on top of it, right? And these are glyphs and diacritics or whatever, diacritics, or I don't know. I'm one of those ASCII speaking English guys. I have no fucking idea what I'm talking about. The little fancy hats and the little doobly-doos that the Russians like, and the French are all about them. Yeah, accents. There's all different kinds of fancy words for those things. And by the way, my wife is Turkish, so there's a ton of fancy shit they have in that one too. But all of those things can also be up to 4 bytes. Those are part of the language too, and they can modify characters that come after them or before them, and there's all kinds of rules about that. Then there's a whole process of normalization for it. But you don't know whether or not you're receiving 1 byte of the character or the entire character, right? So that's what Rust is saying here. And what I mean by that is you have to make the decision how you want to process it as a programmer. And because you have to make that decision, there's 2 different ways to iterate over a string. You can convert the string to a vector of bytes, process it 1 byte at a time. You can tell the Rust, I want to process the string as an array of characters, or as a vector of characters. Okay? And Rust is effectively saying here, when you ask for an integer, you ask me to get the first element in the string. I don't know which one you want, and I'm not going to make an assumption. Just a language design choice. Let hello equal string from Ola, and then let hello equals, I don't know, some Baltic thing. I'll take your word for it. Whatever. Acrylic, yada yada yada. Cyrillic. Is that a Cyrillic? Okay. Cyrillic. We have hello equals and then Cyrillic, and then answer hello equals 0. Okay, now in this case, you already know that answer will not be 3, the first letter. Returning 208 is likely not with user. Okay, I agree. Yes, okay. So this doesn't actually run. I was making sure that didn't run. Okay, and it's telling you why it doesn't run. It doesn't run because, and they're giving you the reason here. And I saw that. I should have seen that the crab thing, because the crab thing tells you on the right-hand side it doesn't run. And I was reading that code and saying, why doesn't it run? So what's actually happening here is they're telling you what I just told you, right? That users generally don't want the byte value returned, even if the string contains only Latin letters, but sometimes they do. And it's not clear that you would want the characters returned. And by the way, like, let's say that you're processing a string and you do want the bytes returned or whatever. Generally, you can just go rs and you would say string. And it'll open up the string type, and then you come down here and you hit this guy. And on the right-hand side, you can see all the different things you can call it into. And then you say, OK, I want bytes. So you just do a search for bytes. And you have as bytes and into bytes, and as bytes and bytes. And I'm just telling you like what I would do here. And then my point is just simply say you don't have to memorize this. You just have to know how to use the documentation. Because like they even said it, most of the time you don't want to process things by bytes. That's probably a true statement. When you do, open up the documentation and search for bytes. Russ makes it very clear. Returns a byte slice of the string's contents. This one takes self and it returns to you the vector of bytes, right? So I already said that a string is a specialized vector that has UTF validity ensured when you construct the type string. And I said you could go from one to the other. Here's how you go from one to the other. And notice that this implementation does not require you to copy anything. This just changes the type. So you lose the stringiness of it. It is now a vector of bytes. You can do whatever you want. Now, if you want to go back from this vector of bytes now to a string, you have to, again, revalidate your UTF-8. But there's probably other methods here, too, to handle that. Into bytes converts a string into a byte vector. OK, I may have been wrong. Wait a second. Yeah, OK, well, one of them is owned, one of them is not owned. OK, we're leaving that out. We're getting too far in the weeds on that. All right, let's scroll down. And here we have, OK, good. We're in the wonderful world of Hindi. So we have this guy right here. I always like watching how bad Chrome is at copying different languages when you throw them jamming together, Especially if it's like an Arabic word and it's in the middle of like a left to right thing. You copy it and your whole page gets highlighted. It's bizarre. But here we have a Hindi word and it's written in some special script here. And they're trying to show you that these above, they look like it is 4 characters, right? You see 4 characters, but it's all of these bytes underneath. Right? There's far more than 4. That's the only point it's trying to drive home. And the reason for that is likely that we have both the base glyph and then we have something that's decorating it, an accent or something like that. So if we process it as characters, right, this is another good question. The 18 bytes is how the computer ultimately stores the data. If we look at them as a Unicode scalar values, which is Rust character type, they look like this. So the above string, right, which is 4 characters long, if we look at them as if they're characters, we get this stuff back. Why do we have more than 4? Why do we have 6? Right? We have 6 because the 4th and the 6th are not letters. They're diacritics. So this is where I talked about Unicode has these things that are, you can think of them like characters, but they actually decorate another character. And they're showing you that there. They're showing you that in the above string, which has 4 characters, when we iterate over them as if they were characters, we actually get 6 things back. Why? Because characters is treating each different UTF-8 thing as a unit. And it doesn't know whether or not the unit is supposed to decorate something after. There are Unicode normalization libraries that handle that, if you really want to geek out. OK, and they're showing you here, this is probably what you want. You probably want the grapheme clusters. That is the name for the UTF-8 character and everything that decorates it, right? Which, by the way, just to talk about like how complex this can be, I think you can have up to like 2,000 things decorate a single piece, a single character. You can have like 2,000 things that decorate one character. There. What's up?
It's called Zalgos.
I have no idea what Zalgos is, but I saw one guy who wanted to see how big he could make a single tweet, and the tweet was like 200 characters, and it came out to be something like a meg or something like that. And the reason was that he spent 2,000 characters to decorate every single letter of his tweet, and you highlight it and your browser comes to a screeching halt. It's a nice trick. And the reason is because when Twitter made the platform, they said, we're going to limit these by grapheme clusters. And he said, well, let's see how far I can abuse a grapheme cluster. And he got this unhighlightable mess. You know?
Evan, you knew the term grapheme clusters before?
I had no idea. No, I just read it. No. I mean, I knew the concept. I knew this concept of like a decorated thing, but I don't remember these terms
Yeah,
enough.
That term is new to me as well.
From a UI
Yeah.
standpoint, you should
Yeah.
just make the graphics cluster.
I think a grapheme cluster is the same thing as a grapheme. I don't think there's a difference, because you cannot have a decorating diacritic in isolation of the thing in which it's decorating, because sometimes the decoration requires it to act differently based on how it's decorating something. So the grapheme is what you present to the user as one unit. You know? So I don't know what it means to have a grapheme cluster versus a regular grapheme. But a grapheme is the right word for the pretty thing. You know? All right. A final reason Rust doesn't allow us to index into a string to get a character is that indexing operations are always expected to take constant time. This is also, I think, bizarre. But whatever. I don't think that that's very consistent with the language. There's certainly nothing about the trait that makes that take constant time, but certainly it could be one argument, you know, which is that when you want to know what the second character is in UTF-8, you actually have to iterate through the first. If you want to know what the 200th, I would say the 200th grapheme is in UTF-8, you'd have to iterate through the first 199. That is indisputably true. I just don't know whether or not it matters that, you know, if you can't do that in what they say linear time, right, or in static time, you can't make that jump, then you can't use the index trait. All right, so now we have this fancy Cyrillic. I pronounced it right. And then we have this hello, and we're saying we want to pick out 0 up to, but not including 4, right? So this is going to get the 0th index, the first index, and the second index, and the third index, not the 4th index. So that's what we're doing there. And this is all going to come back as a string slice. All right. Earlier we mentioned that each of these characters will be 2 bytes, which means it will be 3A. Okay, so, or whatever that is, 3 Russian A. The point here that I would make is that this is not guaranteed to work, right? And this gets back down to what I said earlier. And the reason why I said it earlier, even though it sounded like I was shitting on Rust, and I just said it doesn't do this because of language design, is because it's not entirely consistent, in my opinion, with the way other parts of the language work. Here's a great example. The string slice will work as long as you end it on a byte boundary. Right? What does that mean? That means you can't cut off in the middle of a Unicode character. You have to take the entire Unicode character, then you can take a string slice of it, and it may or may not do what you want. And we just saw an example where it doesn't do what you want, right? Because we saw that one where we had those 4 Hindi characters, and there were actually 6 characters underneath, right? So if you cut it off at the diacritic, what do you get? A magnifying glass, right? I think that's actually what we got, right? So right here. So if you wanted the first 4 characters here, you're going to get these 4. You know, this, and the magnifying glass. But it'll work. You'll have a string slice. And that's why I'm saying you just got to make a decision with the language. And if you are cautious and you want to find a better way to process things, there are better ways to process things than to use this. All right. 4C in 3A characters, print line C. And this is going to print out all the different character representations. This is going to get us the magnifying glass. And if we print them out as bytes, we're going to see all of the different bytes for it. Strings are not so simple. Yes, that's true. They're complex. OK, storing keys and associated values in hash maps. This is another area where I like to bring it up with Perl programmers, right? Hash maps in Rust are beautiful. And when you see what Rust is doing, you'll start to think, well, why isn't this optimization in every language? Because Rust has it, and it's very elegant. And I think we're going to get to that shortly. It's actually one of my favorite parts of, I think, this chapter. When we do this, creating a new hash map, we can see here that we are inserting 2 key value pairs. The hash map must own these key value pairs. And I will say one other thing is somewhat annoying, is does anyone know what an actual hash map means? What does it mean? Should I explain that?
Maybe a collection of key value pairs.
That's good, but there's a lot of ways to collect key value pairs, right? That's just a map. The keys are hashed. What does that mean when I say the keys are hashed?
Every time you store a value, the value gets hashed, and then that hash value becomes the key.
That is actually not correct in Rust. I'm going to go into why. But I want to talk about, I want to get on a point that you didn't hit. Go.
So my understanding is that your key is hashed to know where it is stored in memory. So when you provide what it is, it's going to take constant time to find it. That's my understanding.
Yes, that's good. The point that I would make here is that we use this term called hash. No one has actually specified what it means. What does a hash mean? Give me an example of a hash.
The offset of 256.
CRC.
Like,
A CRC is a good hash. There we go. But it's the one that no one here is going to know. So give me a hash that someone's going to know.
SHA.
There we go. SHA, MD5, this is a hash. Basically the way these things work is you give in data, you get this unique thing out of it, right? And you hope that given any series of data as the input, you're going to get a totally random output. Why do you want that? Because you want to know that the hash is well balanced, however it represents it in memory, right? So you want to know that if I give it, let's say the input is the fox jumps over the brown fence, and then you give it another piece of input, and it's the fox jumps over the brown fence, period, that these two strings, despite looking very similar to you, represent totally different hash values to the computer. That's one of the elements of a good hashing algorithm, is that it's got this total randomness that is not easily predicted by the values, right? So the point that I'm trying to make here is that because that is how it's getting stored under the hood, right? This stuff here, string from yellow, string from blue, has to be hashable. There are some things that are not hashable. There are some things you can't calculate an MD5 from. And because of that, you can't use them as indexes in Rust. You may be able to do it in whatever language you're used to, where they cheat. And they say, well, if we can't hash it, we just take the memory address and we give that to the hashing algorithm. Rust doesn't do that. So you're going to see a lot of times you try to create a hash map over a type that's not hashable or over your own type, and you have to tell Rust how it's going to hash that type. If you create a struct and you want to index the hash by the struct, you're going to have to tell Rust how to hash your struct, right? So there's those kind of complexities. They exist at higher levels, right? But what we want to do here is we're going to say team name equals string from blue, and then we're going to say here underneath it scores.get team name copied unwrap or. This is going to get us the team name. It's going to make a copy of that value, and it's going to unwrap it, getting us the actual value, or it's going to set it equal to 0, right? So the score will either be, if the team name has already been set, it's going to find the score for the team, or it's going to start them off with 0.
Is there a particular reason it's using string structs instead of slices?
Because it has to own it. That's a really good question. That is a really good question. The hash map must own the data. Okay? And by the way, this will be really annoying to you because you're not going to want to create all these different strings for it, and Rust is going to make you do it. So you're either going to have to say, in this case, like they're doing, string from blue, string from yellow every time to create an index into it, or you're going to have to do quote, blue into, and then Rust will say, I need to make this into a string. There's different ways, but I'm saying the end result is you want to use a literal, and you simply can't. Rust has to own that type. Okay. So here we're inserting and we're iterating over this hash map. And again, this is just using the iterable trait under the hood. Hash maps and ownership, this is exactly addressing what you're talking about. It must own the type, or it must be copyable. See? The values will be moved and the hash map will be the owner of these values, as demonstrated in this listing. Okay. Updating a hash map. Overwriting a value. Although the number of the keys and values is growable, each unique key can only have one value associated with it at a time, but not vice versa. Yes. When you want to change the data in a hash map, you have to decide how to handle this case when a key already has a value assigned. You could replace the old value with a new value, completely disregarding the old value. You could keep the old value and ignore the new value. Yes, okay. So now we're going to see how we update different values. The first one that we're going to cover is overriding it. So here we have scores insert, and we are inserting two different values, two of the same values, blue and blue. The first time we insert it's 10, the second time we insert it's 25. And what they're showing you is it gets overridden by default, right? The second way we had to do it is we're going to create, by the way, this is called, let's ask one more question just for geek cred here. When we try to insert two values into a hash map and they're the same key, underneath the hood, we are creating a what?
Collision.
Boom, a collision, right? This is also how MD5s and SHAs work when they result in the same value. You create a collision. You want that collision to be something that can only ever be created if the input is the same. You create a collision. If you have an area to where you can create a collision using two different values, you have a real problem. And when you have an area in which you can create a collision using one value and fabricate another value, right, then you have an insecure hash. This is why the MD5 isn't used. So to hit on security, about 5-6 years ago, something like that, Google showed that they could take the MD5 of a PDF and they could create another PDF, right, that had the same MD5 sum and different forged content. And that was considered a grave, serious vulnerability. And it took them something like 3 weeks of computation time and $1 million to do it or something crazy. But they proved it, and that's actually what got the world to migrate off of MD5s. Because it was actually the proof of concept that the nerds wrote down in math world and place was shown to be something real. And now if you use MD5s, someone uploads a PDF into your system, you store it as the MD5 sum. Now you have someone else that can upload a new PDF in the system, can say something totally different, it gets stored in the same place. Bad idea, right? So that's why people moved to SHA, and now SHA is insecure. So we're moving to SHA 256 and SHA 512 and other things. All right, so this is where this is beautiful though. Okay, so let's go over this, right? This is really cool. Rust has this thing called entry, right? And entry, it hashes the thing you give it, right? But then it doesn't just return the value. It returns a new type called entry. And what's cool about entry is entry stores it caches the hash that was already made, right? So you give it this input. You say, I want to store in this hash map key that is abracadabra and a value that is foo, right? And what I want to do is first I want to see if abracadabra already exists. If it exists, I want to get that value. If it doesn't exist, I want to initialize abracadabra to foo, right? If you were to write this in, as far as I know, any computer programming language, that hash value has to get recalculated twice. The first time you hash it, you say, get me the value. The second time, when you say, if it doesn't exist, I want to set it, the language is going to rehash it again. So you've paid the price of hashing that value twice. Rust doesn't have to do that, because Rust can say, the first time you get that value, I want to hash it. Then I'm going to return an entry. And that entry provides this or insert option on it. And if you call or insert on an entry, the entry is going to store the hashed value. Rust doesn't have to do the work again. Now Rust knows what the value hashes to. It can insert it is a very quick operation. You've eliminated one hashing operation. Right? This is where you're getting a lot of like the cool functionality of Perl and Python and Ruby and these other languages that have hashes or B trees like this that do this kind of stuff, but you're finding it to be much more efficient. Why? Because there's a method to get the actual thing that represents the hashed value. It's exposed to you as a user, and you don't have to calculate it twice. All right. And they don't go into any of these details, but if they don't go into these details, it doesn't really make sense. Why would you ever want to use it? What's the point of entry? Why does it exist? Why do you have entry or insert? It doesn't. None of that's going to make sense if you don't talk about it not just being much cleaner in logic, right? The reason why you do this is because you're trying to optimize you're trying to optimize a hashing operation. Okay, updating a value based on the old value. So here we have text, and we're splitting it on white space. And now I am taking this hash map, and I am looking the entry for the word. And if the word isn't there, I'm inserting in 0. So we're counting the occurrences of a word, And if the word doesn't previously exist in our database, then I'm inserting 0 and we're starting off the process. All right. OK, yes, here's one point I should have done. When we say here text.split white space, in this case, rather not here, count. Count equals map.entry word or insert, right? Map is mutable, right? The entry that you're getting back on the mutable map is going to provide you the ability to write to it, right? So when we say here or insert 0, this is what gives us the ability to dereference the count and add equals 1, right? This plus equals 1 is how Rust says plus plus, or how it adds 1 to the value. So that's what we're doing here. We're actually saying we want to add to the reference of count. OK.
Well, how did count become something that needed to be dereferenced? How did it become a reference?
Because or insert is returning a reference to the value.
OK.
See, the or insert above, the question is, what should or insert return fundamentally, right? Or insert could return the argument you gave it, but that would be really stupid because you just gave it that argument. So why would it just tell you what you gave it? So if you're going to make or insert give you back something useful, what are you going to have it give you back? And in this case, it's giving you back the actual reference to the value in the hash.
Okay.
And remember, too, that when you're looking at a hash, only the key is hashed, right? So the key is hashed. The value can be whatever you want. So when you're saying map entry word, this is getting hashed. Or insert is saying, at that hash value, I'm either going to get back what I had there, or I'm going to initialize it to 0. But I'm going to return the reference to that value so we can later modify it. OK. Hashing functions, yes. OK. This is also really geeky, and some people love this. I'm not going to show you any code about this, but I'll say it at a high level. When we started this off, I was asking you to name something that would communicate to people what a hash is, and you rightfully said CRC, which is a very popular hashing mechanism. There are lots of them. SIP hash, which is what Rust uses, is now the dominant by far. There's actually a benchmark for different hashing algorithms, and SIP is considered one of the fastest, most secure methods of doing this. But different languages have different methods for it, and sometimes you don't care about security, right? Sometimes that's not your concern. So there's a lot of cases that's not going to be your concern, especially if you're competing in a benchmark game, right? Then you definitely don't care about security. So how do you make a hash work faster, given that you don't care about security? There are ways in which you can do that with Rust. And in fact, Rust makes that very easy to do that. You can actually pick the hashing algorithm that's used if you want. If you don't want, Rust has its own hashing algorithm. It'll use it by default, SIP hash. But there are ways in which you can replace that. And there are hundreds of hashing algorithms on crates.io. And you can go look exhaustively about it. And basically, anything a dweeb writes in a white paper that he uses to get a PhD will have a crate on Cargo, or crates.io, and you can pull that down.
The whole purpose of the hash is security? I know it is normally, but...
It's a compromise over...
or is it a way to generate a unique ID or reference? Well, I guess the key is already that. Yeah, I guess.
Map, it's speed. It's not speed.
Yeah, speed is usually a high priority, but in Rust, security is the first priority, right? So Rust is a blazingly fast language, but it never sacrifices security for it. In some languages, they do sacrifice security for it. However, what I would say to that is, when you're looking at how to evaluate a hash map, hashing function, your first concern may be security or speed or space, right? Let's say you're running it on an embedded system. I told you you could program wristwatches in Rust, right? If you want to have a hash map on a wristwatch in Rust, you may be very concerned with how quick you can hash those keys. So all of these things could be what your concern is. And based on that, you could use a different hashing algorithm. But for your purposes, it doesn't matter, right? I mean, when you hit the level that matters, you'll be making a lot of money. So the SIP hash, the default, is totally fine. And I think Perl uses SIP hash and Python uses SIP hash. So these are very popular, universally useful language things, hashing algorithms. All right, error handling. So we talked about errors in the context of a result. Remember, what is a result? Who remembers what a result is?
One of the enumeration options was the second. Like, if you don't get a valid result, instead of it crashing out, you get this.
Rust has.
With a generic error.
Okay. It's an enumeration. You're right. It's not a struct. It is an enumeration which can be constructed with OK or error. Both of those take either a response to represent OK, like a status code, or an error, which could take an error message or an error struct, right? But fundamentally, the result is an enumeration, just like an option. The difference is option represents success with some, right? And it represents failure with none. So there is a translation between an option and a result, and you can do that. Like Rust has that ability. Why? Because these are two different collections, and you can treat both of them the same way. So when I say you can treat both of them the same way, here's another great example. This may not always make sense. I believe you can call OK on an option. What is it going to return? It's going to return the sum value, right? OK. So what I would say here is result is an enumeration. It has two different type constructors. One of them is OK. One of them is error. They both take an argument. That argument represents the different status. And whenever you handle a result, you must handle both of those. Or tell Rust that you want to be stupid explicitly. OK, there are other ways in which we can handle errors. We can panic, and then we don't ever have to do this. You can write very complex programs using panic, and sometimes you see that when you want to write embedded Rust. You'll see this kind of stuff, where the release, you're breaking it down to abort. And what does abort do? Well, there's a process called unwinding. I'm not going to get into it too much, but basically, when you call different functions in a program in C, what it does, it's not actually a C thing. It's really a processor thing. What it does is it has different frames on the stack, and they represent different function calls. And you can unwind those different function calls and say where the problems are at. This was called by this, which was called by this, which was called by this. We call that a stack dump, right? Stack trace, stack dump. That process of unwinding the stack is very common in many languages. The Rust is telling you that you can make your program smaller by doing this, right? Actually, it's not memory that the program was using, then you need to be, OK, yes. It's not actually telling you why you would do this. You do this to make your program smaller. If you say panic equals abort, you no longer have to have the code in your program to unwind the stack. So you can do that and make your program smaller. Then this panic becomes very stupid, right? Thread main panicked at this, and then crash and burn, and it doesn't tell you anything. So this panic macro is one method of throwing a panic, right, without actually using unwrap. You could create an error of result, right? Result is an enumeration which can be created with OK or with error. These are two type constructors for that enumeration. We could create an error and unwrap it and do the same thing. Panic is a macro that gets that done a little bit quicker. OK, using panic and backtrace. So we have this. Yeah. So the backtracing stuff in Rust is really cool, and you can do way more with it than this. But this is relatively good. This is showing you here what it looks like to produce one of those backtraces, right? So you're going to start off at the bottom, which is going to tell you this is the coremost thing that happened, the furthest thing away from you. Call once was called. Call once is what executes main. right? So you know there is some, main doesn't get executed by default. It's not magically executed. There's actually something that gets executed before that. It's called call once. And C, it's called entry 0. And then main gets called, and then this thing gets called, which is the indexing operation. And then the slicing operation gets called, and then you do this thing, and then it just gets crazy. And then eventually, this is probably where the error actually happened. And then you do the panic for the balance check, and the panic for the format, and then you do the Rust begin unwind. And you can process all that stuff, and there are even ways in which you can handle it in Rust, but it becomes pretty explicit. All right. Here's what I would say about this. For most cases, unless you're really concerned with the size of your executable, or you're trying to write malware, or you're trying to write programs in which you can reverse engineer and understand easy, you want to learn about that kind of stuff, don't ever use panic like this. There's no point. And I've never used panic like this in any code I've ever written. In fact, if you want to write good code, don't ever use panic at all. Don't ever use unwrap, don't ever use except. Always handle your errors the right way. All right. Enum result, there's what it is. There's our enumeration. There's our 2 type instructors. We've already talked about that. Here we have a file, and we're opening this file. OK, and here's how we handle that, right? So now we have this reading file result, and we have to handle that result. So match is actually what's handling it. And match requires it to be exhaustive. I think we covered that in the last class or the class before that. So we have this OK and this error. And these two are exhaustive on match. That means they cover all possible outcomes. Right? I know that when I run that code, one of those 2 branches will be hit. And that makes Rust very happy. That's what we want. So right here, the error side is getting hit, right? And because the error side is getting hit and you're not handling that error anymore, you're panicking, right? Now, could we handle that error more than this? Certainly, right? But eventually, when you get down to main, it's difficult to make sense of what the program should do at this point, right? So if you have things, the deeper in your stack you go, the more important it is for you to handle your error. By the time you get to main, there's really nothing else you can do other than terminate the program, right? So at this point, that's all they're doing. And in some context, in just this context, that's probably OK. Matching on different errors. OK, so we have OK, and we're matching the file. And now what we're doing is we are storing we're unwrapping error and getting this error struct out. We're storing that as error, and we can further match on that, right? So there is an error struct that Rust has that you can use to represent an error object. In some languages, you use a custom exception for this. They have the ability to extend an exception type, and that has things behind it, like a name, a description. So when you want to throw an exception, you'll throw the default exception type, and you'll provide it a name and a description. In Rust, there is an actual error type, and it has a kind in it. And they're showing you, this is what it kind of looks like. This stdio error kind, right? So let's open this up, and I'll show you. And there's actually multiple of these in Rust. This isn't the only one. But if we do this, come on. There we go. Error kind, it says handling errors and matching on error kind. And it tells you here, these are the types of variants that this error holds. And it should say methods at the bottom. Yeah. See, and these are the things you can do with it. So you can format the errors, you can clone it, you can create it with from. There's different, it's hashable, it has min max, it has all this kind of stuff on it. They're showing you that one of the things you have is this kind. And you can call kind on it, and it's going to return you what it had. So they are effectively opening up a file, and if that file open isn't successful, they're going to get back an error. That error is going to wrap an error kind. Then they're saying, I want to handle 2 of those kinds of errors. Well, 1 of those kinds of errors. If it's not found, then I want to print out to the user problem creating the file. Otherwise, I want to panic. So they're telling you, potentially the file is not found. That may happen as the program normally executes. If it does, I want to just print out that thing right there. Actually, they're panicking. I take that back. They're panicking either way. They're just giving 2 custom panic errors. Sometimes you want to just print out a nice friendly message to your user and say, this is fine. Like for instance, let's say you made a program called RM and you're removing files. And the question is, how do you handle a file that doesn't exist, right? Maybe your users are supposed to think about RM as deleting the file if it exists. If that's the case and the file doesn't exist, you could just say, we're successful. That file no longer exists. Nothing to delete. Or you could throw an error saying, I couldn't remove the file. Had different permissions or something of that sort.
It's always the first case.
It's always what?
I've never encountered a case where you can it doesn't exist.
Where you can't, it doesn't exist? Here. cd temp, rm. In this case, cannot remove this file, no such file or directory. But
from a user standpoint, I don't care.
yeah, from a user standpoint, you may not care. So you may just want to swallow that error and say it doesn't matter. OK. Matching on different errors. So here we're showing, this is what we just showed. Alternatives to using match with result. There are other things we can do here. Here we are taking this and we're saying unwrap or else, right? Unwrap or else is effectively going to give us back the success if we've got it, or we're going to give it a method to handle the error. And this method to handle the error is called different things in different languages. You can call it a closure or an anonymous function. And this is the weird syntax here. We take name and we have a body. And what we're going to do is process that body here. So this is just the syntax for an anonymous function in Rust. And does anyone here come from Node or JavaScript? OK, we have only one. Oh, that's sad. If you have Node or JavaScript, you've seen it in parentheses, right? They call it I think it's called the fat arrow method or something like that of creating a function. You can create these anonymous functions. You just say, this is my argument, and then you say equal sign, and then you have the angle brackets. OK, anyway, so unwrap or else is going to give you the ability to write a custom function that handles the error. Otherwise, it's just going to give you back the result. So they're just showing you there are different methods of doing it. And the unwrap or else, to bring this all together, this is working on a collection, right? Because the result is effectively, you can think of that as a collection. It will also work on an option. I believe you can say unwrap or else on an option. Then you're either going to get back the sum variant, or you're going to have to process the error. OK. Shortcuts for panic or on error. Unwrap and expect. OK, we've already talked about this. I think we already covered this in another class. Rust forces you to handle errors. If you don't want to handle them, you can shortcut the panicking component by just saying unwrap. Then Rust will say, I got an error, barf it out to the screen, and then you're done. You don't have to handle the error further. If you don't want to do that and you want to be slightly nicer to your users, you can still not handle the error properly, and you can say expect. And then you can give them back something in which represents that error, a string or whatever, and it'll put that out on the screen. Both of these are highly looked down upon in the Rust community, and all beginners start off with them. That's how that works. Here they're providing expect, and it's going to provide this error right here. Hello.txt should be included in this project. OK, propagating errors. This is the right way to do it. So here we're reading username from the file, and we are representing the result with a result. That's confusing. We are representing the output with a result type, which is an enumeration. That enumeration, if it is OK, it's going to return a string. If it is an error, it's going to return IO error. This is a way of showing that the result is strongly typed, that the OK side of that result can only ever be represented by a string, that the error side of that result can only ever be represented by IO error. You're telling your user, this enumeration, you have to handle both of these types. Because OK constructs with a string, error constructs with an IO error. So this is what the user is going to get back when they call this read username from file. What we do here is we say, let username from file equals, and we file open hello.txt. This is going to give us back that result. We're going to match it. If we have OK file, we're going to return the file name, right? If we have error E, we're going to return error E. We're just going to propagate that error upward. We're going to allow it to bubble up to our user. Why is this nicer? Because if you do this, your user can decide how they want to handle the error. Now, in Rust, as you advance further, you will stop propagating errors like this. right? You will provide a different mechanism to handle errors. Why? Because what they're doing here is they're saying, I want my users to handle this error as if they were using this file system call directly, and they were getting back their own IO error. That is far nicer than any option we've seen so far, but it is still somewhat of a pain in the ass for users, because now they have to read what every library you're doing is representing their error, so they can handle all of it, right? There are better methods to do that, and we'll go over them later. But this is really good for now, because now you're giving your user, even though it's a pain for them to do it, you're giving them all of the power that you have. You're not taking anything away from them, right? Username equals string new, and we're doing the same thing here. We have username, file, read to string. Now read to string is also going to return an error. Now here's the reason why this works. It works this way. This function works because IO error is used by the standard library for both file open and read to string. These are both in the part of the standard library that they use the same error. But this is not always guaranteed to be true. So this is a crafty example where they pretend like it's this simple always. But this is really nice, because if it is this simple always, then when your user calls this, they need only handle IO error. And if either one of those two things produce an error, because they produce the same type, that's what your user is going to get. All right.
Is there ever a case where you don't know what kind of error you're going to get?
No, because it's a strongly typed language. You always know. Yeah. But sometimes you know you're going to get two different types of errors. And the question is, how do you represent both types to your user? And the short answer of that is you create a God error type for your library. Generally speaking, a good library has one error object that can represent all of the errors the library generates. And that error that your library generates may include the original error object and a description of the error. And then you can give both of them to your user. They can use your string value, or they can look at or ignore the actual underlying error. So this is why Rust is such a nice, elegant language, because creating that God error object is super simple thanks to macros. But it is a type-safe way to represent all of the possible errors your program can generate. All right. So read username from file. Here we are opening the file. We're creating a new string. We're reading it to the string, and we're returning the OK username part. And the key here is this question mark operator, right? And this looks like a lot of voodoo. Again, not much voodoo underneath the hood. But what this is actually going to do is question mark says, if I get back the error type, just return it. Return it. And what's really nice about this is that we have this concept in Rust of, can a type implicitly get to another type, right? And if the type you get can implicitly get to the type that you're returning, Rust does all of that for you. So if you create this God error and it can represent all the errors in your program, and you say every function returns either my result or the God error, and the God error thing has the ability to convert any error to it, then the question mark works and everything just flows. You know, the question mark will convert the error return into the right-hand side of the result. Rust figures it all out for you. All right, here we read the username from the file, and now we have the question marks, two of them, returned in the same statement. Totally fine, right? So now hello.open can return an error. If it does, the program returns that error. Otherwise, we call read to string on the result, the OK side of that. And if we get an error, we return that error. And what's even more beautiful is they're not showing this here, but in this case, read to string is taking the mutable string, right? Sometimes the thing that's returning the last error may return a value if it's OK. So you could actually say, like, you know, let my data structure equals, you know, file that open thing, and then, read, and then still use the question mark. And it'll just bubble up the error if it exists. Otherwise, it'll take the OK value. It'll unwrap the OK value. Because after you use the question mark, if you don't have an error, it unwraps the OK side. The result side that's not the error. Does that make sense? Cool, I guess. Ask questions if it's not making sense. All right, here we have a result, and we're returning the string IO error. And what they're showing you here is that when we call read to string, what is it returning? No.
Read to string.
Contents of the file.
No. Read to string is returning a result, right? Because you must represent the error side and the OK side in that result. What they are showing you here is that if your program is returning the same result that read to string returns, you don't have to handle the result. You can just make your return type the same as that return type, and you just simply give it back to your user. It just becomes a shortcut. So in this case, I'm telling you read username from file is going to return this result and this string IO error, and I'm giving you an implementation that returns that. This fs read to string hello is going to return this result string IO error, or something that can get to that. And Rust figures out the rest of it. So you don't have to use a question mark here or anything. Because if you use a question mark, what would happen if you used a question mark here?
Work the same.
Wouldn't it what?
Work the same unless it actually throws an error. I know what I'm right?
No. If it throws an error, it would work the same way. If it doesn't throw an error, what happens? I just said it. What does the question mark do if you're not throwing an error? It returns, who said it? Who got it? Who said the word?
String.
Unwrap. Who said the unwrap? Okay, there you go. I thought, geez, you were pitching that way in the back. You were slouching like you wouldn't believe. All right, so the OK side of that, right? The OK side of that gets unwrapped, which means you have the value. But here's the problem. That's not returning a value. That's returning a result. So how do you get the value back to a result? You have to rewrap it. What do you rewrap it in? In OK, right? Because the result is the enumeration, right? The enumeration result can be constructed with OK, that's one type constructor, or error, that's the other type constructor. So if you wish to construct a type of result, you must use the type constructor OK or error. So in this case, if we use the question mark, right, we will give the error to that above, just as it expects. But if we get the result back and it's not an error, we have to rewrap it. And the takeaway here is sometimes you'll be developing programs, and you'll notice that all of your programs, your functions that return result, are rewrapping everything in OK. And you'll start to say, that is awkward. Why do I always have to do that? And that's what they're trying to show you here. There is another way that you don't have to do that. Sometimes you just get the right type back, leave it alone. Don't fuck with it. Just give it right back to your user, and it'll make total sense. You know? And a lot of this stuff I learned by live coding in the Discord channel years and years and years ago. So that's a good way to learn, is that someone will be there, they'll look over your shoulder, and they'll tell you when you're doing something stupid. Because the compiler doesn't have a single problem with that. Some people like writing code that way. Some people find this to be too much voodoo. The fact that they're not actually doing anything with the result. They're just handing the whole result, OK and error, back to the user. They're allowing OK to bubble up too. Some people don't like that. So you could say, let OK, or let result equals fs read to string hello.txt, and then right below it, OK result. You know? That would be totally fine. So compiler won't advise you on which one of those looks better. But there'll always be some neckbeard in the Discord channel for Rust community language, and they'll tell you, you know, this could be shorter. This could be shorter is always how you get yourself into trouble as a programmer. All right. STDFS file, we're going to say here the main greetings equals file open, right? And this is not going to run because we are not handling the error side of it. Oh, no, I see what they're doing. They're trying to show you that the question mark has to be able to represent the error side, right? And this is also a language choice. This is, in my opinion, this could have been done differently. So the problem here is that in main, main, I believe, can actually be typed to return a result. And then what it will do is, if main is typed to return a result, if it errors, then the program terminates anyway. But by default, main is not typed to return a result. It is implicitly typed to return a status. That's how every program executes its main function. They expect it to return 0 to 255, representing a status code. So what happens if you try to use a question mark in it? Rust says, I don't know how to get this error side of the result to 0 to 255. And that's what it's telling you here, right? Cannot use the operator in a function that returns and then nothing, right? Actually, what they're actually telling you is I was wrong. Main by default returns nothing. You can make main return an integer though too. So the fact that main returns nothing means that there's no way for you to return a result, an error side out of it by default. OK. Last character of first line. Here we have text string, and we have an option character. This is going, what, last character of first line. We take text, right? And what lines is going to be doing here, let's go through this. So we know that text is a string slice, right? And we're calling lines on it, right? So let's look through this. What is called right after lines? Next. What does that always mean about lines? It's returning an, does anyone know the word here?
Vector.
No? You're able to call next on it, which means it's a, yeah, no, I mean, an iterator. If you can call next on it, you're iterating through it. Next always means iterator in every language, JavaScript, Python, Rust, it doesn't make a difference. If you're calling next on it, that is universal for saying I'm iterating over it, right? So we're calling next on it, which means we're iterating over it. That means lines is returning an iterator. What is the lines iterator doing? It is iterating over the lines in the string slice, right? So when you call next on lines, you're going to get one line back. And they're using a question mark. So if you don't get a line back, you're going to return none, because this is an option character, right? So an option character can be created by using some and a character or none. So the question mark will return none if you don't get a line back. Otherwise, you're calling cars.last. And I can tell you right by looking at this, last is operating on an iterator, which means cars has got to be returning an iterator. So cars is going to know how to iterate over a single line. It's going to be looking at some representation of characters in that line. So we have text converting to an iterator of lines, looking at the first thing, returning, if we get nothing back, if we get something back, we're going to be returning Python, which is going to return an iterator, we're going to look at the last character. This process of stringing all these things together to return iterators, right, to process results, then we call cars, we get another iterator back, we process that. This is how we string together these things that modify collections. And this gives you the vocabulary to reason about all of these crazy collections, even ones you haven't seen implemented, based on a simple grammar. And the grammar in this case is, next means I'm operating on an iterator, and last means I'm operating on an iterator. And what does the implementation of last look like? It could look totally different depending on how that iterator is written. In some iterators, I may be able to say last and get to just the very last thing. In other iterators, I may have to iterate over every single thing until I get to the last element, and I exhaust the iterator. Last may be implemented differently for different iterators. All right. So here, did I miss anything I want to go over? I think I already went over that. OK, good.
Is there ever a case where you need to use the question mark multiple times because you're stringing together iterators?
You mean like question mark?
No, I mean like something iterator question mark, some other thing iterator question mark, some other thing iterator question mark. You can just keep going.
Sure, yeah. You use it with question mark multiple times, yeah. Sometimes you'll use it after every different command to the collection, because every one of them will return a result. That's quite common, you know. So you just gotta keep in mind that you're using syntactic sugar here. Am I returning a result? If I am, can I get that to the error type that I'm returning? If I can, use a question mark. So yeah, you'll see a lot of them in your code show up. And by the way, this is why Rust is doable, you know. If Rust didn't have this type of functionality, it'd be a pain in the ass to write Rust. You'd have to handle every different error type yourself and say, how do I get it to something I can return? You know, Rust is nice because it has this concept of implicitly converting the errors for you, and this concept of, with a little bit of sugar, returning the error right up without you having to write it. And that's why you make these short chains. I mean, like, look at this. Let's just talk, like, look at that. Write me that code in Python or Perl and make it look smaller. I bet it won't look smaller. I bet that's probably as small as Python or Perl can make that code. So you're writing in a language that's compiled, and it's 100 trillion times faster than Perl or Python, and it's as easy to read, you know? That to me is not difficult to read. And I would think that it shouldn't be difficult for other people. By all means, pipe up if you think it is. But that's quite a bit of work we're doing there. We are looking at the first line, the last character in that line. Or I just read the function name, last character of first line, even better. And we're writing all of that in 20 characters. Compiled language, that's type safe. That's pretty good, you know. All right. So we have main, and in this case, notice what we're doing. We are returning a box of a din error. Now, this is something that main can return. And because it can return a box of din error, now I can use the question mark. This is what I was saying earlier. So this is actually how main returns an error type. And this is kind of nice. So in this case, just so we can go over this really quick, a result of this, we're going to get more into this in the next chapter, which we're not doing today. There's 0% chance I'm going to use that today. The box of the result here is telling you two things, right? The first thing it's telling you is if you are successful, we don't need any data. If main is successful, I don't need to show any data. There is no useful way to make main successful and return that to anything. Why? Because Linux sucks. No, but seriously, that's the fundamental reason. The fundamental reason is because when Linux calls its entry point, which calls main, Linux doesn't care about the result type of main on success. If it's successful, Linux gets a status code of 0. That's all it cares about. You can't give Linux back a string and make it care and log it anywhere. It's just not how the operating system's built because of baby boomers, you know, blame them. So there is no useful thing to return from a program that is successful, except status code of 0. That's it. On error, right, we're saying here a box type, right? Now, a box means that the thing is stored in the struct. We covered that over briefly. This is the new part, this din error. And what that means is you are implementing the error trait, right? So any error that exists on the heap that implements the error trait, this syntax will handle. And what will it do? It'll just simply say, if I get an error, return that error status. You know, set the error status to not 0. That's what it'll effectively do. OK. A trait object. There you go. Yes. OK. I'm going to leave that alone. To panic or not to panic? OK, so here's what they're showing you here. They're showing you that we talked about this concept of a program that can panic. When is it always OK to panic? It's always OK to panic if you know you're not going to panic. That's a shitty answer, but that's what they're showing you here. And in this case, it's OK because you have more information than the compiler. Sometimes the compiler doesn't know whether or not you're writing good code or bad code, and you know for certain you're writing good code. And in this case, you know for certain that the error side will never be hit. Perhaps one day, Rust becomes good enough to where it can prove that what you know, it also knows. But until that day happens, you can call this, right? So there's a home address here. We're saying 127.0.0.1. We know that that is a valid IP address. So we're saying parse this string as this IP address, right? And expect it to be true. And if it's not true, panic with this error. We know that error will never be hit. You could just as well say expect gobbly-googly-gook. It doesn't make a difference. Because we know it will never be hit, you can always ignore people who raise an objection. You can just simply say, I know better, and leave that alone. And perhaps, like I said, seriously too, Rust may one day be able to do this in the compiler. And that really depends here on whether or not these things called constant functions emerge and parse becomes one. But guidelines for error handling. The bad state of something, OK, yes. They're giving you some advice here. Yeah. This is just, the bottom line is when you can handle the error, return it to your user, or return something that represents all of your error data. And don't panic it and make the assumption your user wants to die. That's not nice. Creating custom types for validation. Okay, so here we are taking this I32, and we are calling, we have this input called guess. We're trimming it, we're parsing it. We saw this from the counting game. They're revisiting this. Because this is an I32, we are potentially getting a negative number. And yeah. Yeah, I don't think any of this is that important or not obvious. Does anyone see here what they want us to, I don't get why this is important enough for them to show. We have a struct called guess. We have a value of I32. We're creating a new guess. This is the constructor. It takes an I32 and it returns a guess. If the value is less than 0 or value is greater than 100, we are panicking. We're dying because we don't want to handle guesses that are outside of that range. And then otherwise we return the guess a value, and then we have a function called value, and it gets the guess, the unwraps it type. This to me is a horrible idea. I would never do this. The reason why is because if you want to represent a guess as being a potential guess or not, you could use none and then represent your errors with that. None is a totally valid way of representing an error. Not a valid guess. What's up? Well, the question is how, you don't want to assert, because if you assert something, the question is how do you handle that? You need to have a method of handling the error type, right? Or give, what? I know, I'm telling you I would never write this code because panic is bad, right? I'm telling you I would write this code to represent a guess as an option. It's either a valid guess or not. So I would say an option represents a valid guess in a sufficient fashion. You either have some, which represents a valid guess, or none, which represents an invalid guess. And you can give that back to your user. Or you could just create a result type that said the same thing. Anyway, the point is there are different ways of handling errors. You'll get used to them. Whenever you have the option to not panic, the only ever reason to choose the panic is this is quicker and I'm lazy, right? Those two things have value. Sometimes you want to take a shortcut. There is no technical reason to prefer to panic ever. So you can always do the better thing by not panicking and bubbling up the error. All right. Now, we are skipping chapter 10 for tonight because it's already 8:40. Chapter 10 is going to be slightly tough. So I don't think it'll be as bad as I think chapter 3, but it's going to be a little bit more hairy than these two. So I think that we have kind of been at a pretty reasonable pace at the class. Chapter 10, things are going to get a little bit hairy. Chapter 11 will be easy. Chapter 12 will be fun. Chapter 13 will be challenging, but not as bad as chapter 10. And then chapter 14, easy. 15 will suck. And 16 will be fun. So we have a couple of ones that are difficult. The next one that is going to be difficult is the generic types and traits, and the smart pointers one will also be difficult when we get to that. We'll cover that one too. All right, that's what we have to look forward to. Does anyone have any questions about it? Does anyone want to rehash things we already went over in the last classes?
Next week, chapters, what, 10 and 11 probably?
Yes, maybe just 10, but likely 10 and 11.
Okay, at least 10.
Yeah, at least 10. Probably 10 and 11. Depends on how deep we want to go into 10, how much it holds people up. There's a lot there. Cool. All right, any last call for questions? I'm happy to show things off. I don't know what we want to show off. You got any ideas? Oh, you want me to show off like my work in Rust? I do. Let's do that next class though before we do the class. That's better timing. Cool. All right, I'm done. Good luck, and I'll see you next week.